Hi, welcome to a new set of lectures on linear algebra. We are going to start with new chapters, chapter 2 on systems of linear equations. Let's go ahead and see what we can build on top of the material of the first chapter. So, as an introduction to system of linear equation, here I have written two examples. The first one, you see I have a pair of equations with x and y, z in it. So this is referred to as two equations in three variables. The variables, of course, being x, y, z. This is another example which has two equations and two variables. So our variables are x and y. I have just two equations. So before we dive into nitty-gritty details of solving systems of linear equations, and there's going to be plenty of small details to pay attention to, let's go ahead and see where is it that they're coming from. So hopefully that motivates us to pay more attention and be familiar with the variety of items that are going to come up. Well, if you remember in the previous lecture, we were talking about forces. So let's go back in the previous lecture. So we had a situation that we wanted to hang a picture frame from a pair of wires. So the picture frame had a weight W, and the wires were at a certain angle. We wanted to find out what's the tension in those wires. When we solved this problem in the component style, at the very first round we came across a pair of equations. If you look at it carefully, this is a system of linear equations in two variables. The two variables were just tensions in the two wires. So that's an easy justification for a system of two equations with two variables. Of course, linear algebra doesn't stop there. We go toward much larger systems. The question is, well, why is it that we need to do that before we actually start doing it? So let me say the following. So in the very first example we did, we said the best way to explain it or experiment with it is to use one of these force tables you might see in your physics or engineering classes, where you counterbalance three forces. Well, what if you have a lot more than just three items to be very worried about? Here you have a force here, a force here, and a force here, certain angles, and you find out tensions in the ropes and so on. But we can come across more complicated situations. So you can have a bridge. Perhaps you build one of these things in one of your engineering classes, and hopefully then you build something much fancier than that, like this one or maybe this one. Well, if you want to analyze the forces involved here, you are going to be dealing with large systems. In fact, very large systems of equations. Here is a moderate size system you can come across. This is from a manual of a certain calculator. So you see here's a example of a 6 by 6 systems. The variables are A, B, C, D, E, F, and there are a bunch of numbers. We refer to them as coefficients and such. And the question is, well, how do you actually solve this? We are going to explain the methods and the issues involved and build toward that. So how about this? Let's see, let's go to our lecture. Here I have written equations with three variables in them. Where would they come from? So again, it could come from applications in engineering, but there could be also applications in geometry. Geometry is going to be easier for us to explain because it doesn't require you to have taken those engineering classes. So where we have come across this issue once, which is what if you have several planes in space and you're talking about their intersection. So if I have just two planes in space, then the equation that I'm going to have will be a linear system, two equations, three variables. If I have three planes in space, then I'm looking for three equations, three variables, and so on. So we have geometrical motivation for studying these kind of systems, and we have also a lot of engineering applications in mind. We are going to come to those applications later on, but right now let's just lay down the mathematical principles. Okay, next up, you see this word linear appearing all over the place. In fact, is in the title of name of the course, linear algebra. You might be wondering, well, what does that mean, linear? We keep repeating linear equations. So what is meant by a linear equation? That's as opposed to a non-linear equation. Let's go ahead and explain the differences. So example of linear equation will be just like the ones that we wrote. Examples of non-linear equation would be equations that involve, for example, powers, radicals, functions, and so on. So if I have an equation like x squared minus y cubed equal to 5, we are going to call this a nonlinear equation. One clue to that is that if you graph it, the graph does not resemble a line. But of course that definition is only good for an equation with just two variables on it. The full definition is a rather technical one and has a subtle aspect to it, but let me just go ahead and mention it anyway. At this stage, if you have variables and your variables are called x1, x2, x3, and so on, you could have so many of them, but you have to specify how many of them you got. So we write them with subscript as opposed to using different letters of the alphabet, because that's going to be more practical for larger system. Then a linear equation. A linear equation is an equation that can be written, perhaps after certain steps, can be written as some number times x1, and that number, let's call it a1, plus some number times x2, and that number we write it a2, plus some number times x3, and so on, all the way to the very last of them, an xn. If the sum turns out to be another constant number, so in this situation, a1, a2, and all the way through an, as well as b, these are all constants. Constant meaning they do not depend on our variables. If you can reduce your equation to an equation of this format, then you call it a linear equation. Otherwise, it would be non-linear equation. Now it takes a bit of a work to show that this actually is not a linear equation, but most introductory textbook gloss over that issue and don't get into too much detail, and I wouldn't spend that time either here. And if you are interested, you let me know, we'll talk about it. So linear equation, here's an official definition of what a linear equation is. A system of a linear equation then is going to be a set of these things. So again, a specific example, here's a system of a linear equation, here's another system of linear equation. So we know what is a linear equation, we know what's a system of a linear equation. What's a solution set? A solution set would be a set of vectors, a vector being x, y here or x, y, z here, that if you replace them for x, y in the equation, all equation will be satisfied simultaneously. So a set of numbers is going to be called a solution set, provided that if you replace them for x, y, z in the first equation, makes it a true statement, and you replace them in the second equation, also makes that one a true statement simultaneously with respect to the very first one. So that is what the solution set is going to be. Now let's to understand the solution set and see that it's actually a subtle concept and a bit of a problematic concept. Let's go ahead, take a look at a specific example. Item number 5, we are going to talk about the trichotomy for linear systems. This is a grand idea, a grand theorem that says every linear system, regardless of how many equations you got, how many variables you got, has one of 3 possible fates. And here I am going to explain what are those 3 possibilities. The ones that you are most familiar with from high school would be this very first one. Let me go ahead and actually explain what the difference of these 3 situations are, and kind of give a bit of a heads up that the most familiar case to you from high school, that's going to be the least worries for us, and the other ones are going to be the ones that we are going to be paying attention to. So now we are going to describe that trichotomy. A linear system, regardless of its size, either looks like this equation. Let me write it and explain to you what is so special here. X minus y equal to 1. Well, that one by itself, you know from since middle school, that's the equation of a straight line. So I can go ahead and actually draw this. So I'm going to go ahead and draw x minus y is equal to 1. You're more familiar with it as we say y is equal to, say, x minus 1. This is the same thing. Y equal to x minus 1. Let's suppose this is our 1. It's going to look like this. So let me write the equation in the same color as my line. So that is the same as saying y is equal to x minus 1. Okay, how about the other one? So let me choose another color. So suppose I have x plus y is equal to 3. Perhaps you are accustomed to writing it as y is equal to 3 minus x. So it has a xy intercept of 3, I suppose, and looks something like this. So this is our green equation, and this is our blue equation. And when you talk about a system of equation, you mean that you want to be on green and on blue, so you have to be at the intersection of them. So intersection that you see in geometry, same as idea of the solution set that we have here. Okay, so you can either find this thing geometrically, like this looks like x is equal to 2, y equal to 1, and you check it. Well, actually it looks like 2 and 1 actually is the solution. Or you develop methods you know from high school, elimination, substitution, Cramer's rule, or whatever you want to do, that actually gives you your answer. Okay, so that's the more familiar situation. What is not so familiar? Let's go look at the equation number 2. Equation number 2 says x minus y is equal to 2 and 3x minus 3y is equal to 6. When you look at that, doesn't it strike as a bit odd compared to the first one? Let's go ahead and write this. So suppose let's do the same trick here, that x minus y is equal to 2, and then 3x minus 3y is equal to 6. So what is so special? Well, if you haven't noticed, let's go ahead and draw the graph, and surely are not going to miss the clue here. So x and y. So y is equal to x minus 2 here. So let's draw that. So y is equal y is equal to, say, well, x minus 2, or x minus y is equal to 2, and then 3x minus 3y equal to 6. Well, obviously if you divide this thing by 3, it's same as that, so the graph of it will be same as that, and then it's going to just sit right on top of the other one. So that same space is shared by two equations, 3x minus 3y equal to 6, or x minus y equal to 2. They are sitting right on top of each other. So if you talk about intersection or the solution set, the entire line is the solution set. So this whole thing, so let's color it yellow maybe. In this case, this is the solution set. Okay, that is the situation that unlikely that you deal with that in high school or pay much attention to it, or perhaps you put it on the side as a rather weird situation and don't pay attention to it. But as we are going to progress through the semester, we are going to see that this is actually much more interesting to us than that situation. We are far away from that, but we promised that we are going to explain the vibrations of systems, and when we come to the issue of vibration, this is what is going to open the door for us to vibration, not so much that one. Okay, what is the third possibility? Third possibility, what do you think? X minus y equal to 1. Again, a rather weird looking equation that we see here, like almost never shows up in a high school context because of a variety of reasons, but let's just go ahead and treat it the same way. X minus y is equal to 1, and let's put the other one, x minus y is equal to 2. Well, any sane person is going to say, well, if x minus 1 is 1, x minus y is 1, well, then it is not going to be 2. So you cannot have it both ways. This cannot be 1 and 2 at the same time. Well, how does it look? Well, what do you think? This cannot agree with that, which means their lines cannot intersect. And that means what? That means that they're going to be parallel to each other. So if this is x minus y is equal to 1, or if you wish y is equal to x minus 1, it looks like this, and y is equal to x minus 2, it's going to be like this. There is no area of the plane that we are going to color it yellow. There is no solution set. This is an impossible situation. So again, going back, we have a trichotomy. One of three fates awaits a linear system. Either situation like this, or like this, or like that. Now we explained it is in the most simplistic style for a system of two equations in two variables. But it doesn't matter how many equations you got, how many variables you got. Either you have a situation where you have a unique solution, so let's call this thing a unique solution. It's just one set of numbers that fits the bill, or you have infinitely many solutions, like lots of numbers here, such as what? Like if I take x is equal to 2 and y is equal to 0, that's that fits the bill. If you take x equal to 5 and y equal to 3, that's just as good, and so on. You have infinitely many choices. So this is like the 0.20, and if I go 3, 4, 5, this is going to be 5, 3, and of course you could pick lots of points in between and lots of points afterward. So in this case you have infinitely many solutions. And here we said, obviously, if x minus y is 1, it cannot be 2. In this case, we said no solution. Other terminology is used to characterize these cases. These two are called consistent, meaning it's possible, it's consistent to have this thing as 1 and a 3, or a 2 and a 6, and so on. So this one is labeled as consistent. This one is also labeled as consistent, and this one is labeled as inconsistent. Sometimes they might use a word like impossible system and something like that. That is expressing the same idea. So sometimes we go ahead and count how many solutions we have. Here, no solution. Well, if you count how many things you found, so well, I found nothing. 0 solution. Unique solution. Unique. You found just one item. So only one item. Infinitely many solutions. So you can signal it as having infinitely, meaning the number of points that fit the bill is going to be infinitely large. So sometimes this dichotomy, you might refer to it as 0, 1, or infinity choice. Any linear system has one of these things, as opposed to what? Well, you spend most of your college algebra solving quadratic equation. Quadratic equation had like typically 2 solutions. What we are saying here, such a thing doesn't show up, that you'll have exactly 2 solutions. There's no 2 here. You go from 0 to 1 and then you jump to infinity. There's no 2, 3, and so on. Okay, so that is a situation that we need to be aware of, and we said toward the end of the semester this is going to be playing the most significant role for us. We have to wait and see how does that work. Like, we are going to have systems with adjustable coefficients, and we adjust it so that this situation happens, and we'll have kind of like our suns and moons and stars lined up, and when they line up, then magical things are going to happen for us later on. So okay, next up, how about solving these things? Well, let's go step by step. Let's go from simple toward the harder ones. Easy to solve systems. These are, let me also give them the name of triangular systems. Triangular systems are the ones that so easy to solve, or triangular systems. These are the essentially like equivalent of a pre-processed food. Everything is done for you. It's like almost like a baby food or something. So most of the difficulty of the solving system has been removed, and you are just doing a very simple task. Here's a example of that. So y plus 3z equals to 5, and then 5z is equal to 10. We call them triangular because of what? Well, it looks like a triangle. What else do you expect? So what's happening is that there's nothing here, there's nothing here, there's nothing here. So you can think about down here, everything has been wiped out, meaning The first person who came did most of the work, and we are just inheriting an easy situation. Well, what do you do? Well, of course, you go to the least crowded equation, work your way there, and then as this is written, once you find the z here, of course you're going to put it back in the previous equation, figure out the y, and put the y and z and put it back here. For that reason, this style is referred to as a back substitution. Now sometimes you might start from the first one and go to the last, depending on how your triangle is lined up, but let's do it this style. Of course, here right hand side divided by the coefficient, you get your 2 is placed here, and then here you can say y is equal to 5 minus 3z, so it's 5 minus 3 times 2, and then that simplifies to your minus 1. And here your x is 2 plus y plus z, so 2 and then a minus 1 and then a 2, you get a 3. Important thing, how do you package this? Well, your textbook is partial to writing them as column vectors. 3 minus 1 2. This would be the solution of the system. So again, triangular system. By back substitution, you start from the least crowded, go to the other ones, and to the most crowded equation, and solve them step by step. Okay, so that was quite painless. The difficulty arises when, well, for the first person who that cleaned this equation for us, he had to endure a lot more work, and that is going to be one aspect of this course we want to practice, and then see how we are going to do this and how we're going to write it and so on. Okay, so let's separate this. Suppose I had an equation, so the full case now, full case, or the case that person actually encountered before coming here, goes something like this. X minus y minus z equal to 2. Or 3x minus 3y plus 2z, and 2x minus y plus z is equal to 9. Oh, sorry. Well, the question is, if I'm given a full case matrix, all soft gloves are removed and we're just dealing with the full case. What are we going to do? Our plan is the following. Take this and try to reduce it to that. Once you arrive at that stage, solve it the way we did by back substitution, or continue, use the style that we are going to use to create the zeros and pursue that to the final conclusion of arriving at the answer. So we are going to have two methods presented to you, one at a time, and the main idea is, well, how do you get rid of these entries? How do you create these triangular systems so that your system will be easy to solve? So getting rid of these entries, well, the method that we are going to use is going to be called the elimination method. It is essentially same as what you might have done under a different name like substitution and so on, but let's go ahead. So our procedure, we are going to introduce it to you by several examples, is going to be the following. We are going to try to eliminate this entry and then eliminate this entry. By that time, the look of the equation is going to change. There's going to be different set of numbers here, but the idea on the next level would be to go and eliminate this entry as well. once we have eliminated all the entries below the this is called the diagonal. Once we remove them, then we are back in the easy territory, and then we can continue like that. Okay, let's go ahead and learn the methods that are involved here. How do we use elimination? We are going to have one of our equations declared as a so-called pivot equation. The items we are going to eliminate, we are going to call them targets for obvious reasons. So 3 is my target. I want to eliminate that 3 by making use of the first equation that I have here. Well, you have done something like this in high school. If I multiply this thing by -3 and add it to that equation, then I'll have a -3x and a +3x. And when I add the equation, that 3x is going to be wiped out at the expense of the rest of the equation changing. So in my mind, I multiply this thing by -3 and add it to that. Leave this equation as it is, do that work on the side. Then I target 2x. Again, I use my pivot equation. In this case, I multiply this thing by -2 and add it to this, so I get rid of the 2x, and then that equation is going to change and 2x will be replaced by 0. By that stage, we have eliminated these two entries. Then we go to the next level. Next level, our pivot is going to be a new pivot. We are not going to use that anymore, because if we do use it, we are going to mess up the zeros we worked so hard to produce. So we leave the first equation alone. We are going to leave the first column alone. It's all done for now. We go to the second equation and the second column and process that one. So step by step. So in the first step, you are dealing with all of this. In the next stage, typically you are going to deal with this. In the next stage, you're going to deal with that. So a set of nested groups of equations that you're going to look at, and that is how the whole thing is going to proceed. Of course, every now and then there's going to be a little bit of an exception. We are going to explain that later on in more complete examples later on, but let's just go ahead step by step. So the idea, of course, one of the major difficulties is the amount of writing it takes to solve any of these things. So compared to anything you have done, maybe in Calculus 1 and so on, the amount of pieces of data that's in front of you is entirely different ball games. So one of the differences of this course from the previous one is the so-called curse of dimensionality. You have to look at this thing, there's 12 numbers dancing in front of your eyes, and almost never the case in a Calculus 1 problem that from get-go you have 12 pieces to worry about. So this is something that just gets resolved by paying close attention, being patient, not to rush into things, double check your steps, otherwise errors are going to be very costly, and so on. So it takes a different kind of a mindset to handle this. So let's call this one say equation number 1, equation number 2, equation number 3. And what am I going to do here? I'm going to take -3 times equation number 1 and take that, add it to equation number 2. That's how I'm going to eliminate 3x. And then minus twice equation number 1 plus equation number 3. That's how I'm going to eliminate that. We say triple. We don't go ahead and change this. That's going to just introduce more writing, more room for making errors and such. So we do this thing on the side or in our mind usually, and then proceed. So we take this thing, this equation as it is, and then this is going to gives birth to a new set. The first equation as it is just there. Second equation, minus 3 times that plus this, that's going to be 0x, so better be 0x, minus 3y, minus 3 times minus y becomes plus 3y, added to minus 3y by accident, not by design. This one became 0 as well. Minus 3 times that plus 2 makes 5z, so this becomes 5z, and minus 3 times 2 plus 16 makes it 10. If you want to be perhaps not doing it in your mind, you might as well write this: minus 3x plus 3y plus 3z is equal to minus 6. So that is minus 3 equation 1. You're taking this thing, adding to that, and that's what we get. Multiplying this by minus 2, so it's going to read minus 2x plus 2y plus 2z is equal to minus 4, and you are adding it to that, so it makes a 0x. Adding these two gives us a I have plus y, 1y if you wish. Well, let's just write it out. 2z and a z gives us a 3z, minus 4 and a 9 gives us a 5. So again, usually we are going to do these operations in our mind, create our equations here. Okay, now we see something kind of going wrong way for us. What happened is that I want a triangular arrangement. This is, it's not quite like a triangle. My zeros are in kind of a wrong spot. So I have my 0 here, 0 here. By accident, this thing became 0. That's fine. I want this look as a standard look by which I'm going to solve the equation. Of course, you don't have to do this step. I can still go ahead and say this is my least crowded equation. From here I get my z, come and put it here, get y, go back here and figure out what my x is. But perhaps as a mathematician you are going to excuse us for being a bit compulsive. To make this thing look like that, and to introduce you to an operation that we are going to talk about later on, we are going to talk about exchanging two equations. Exchanging two equations simply means shuffling them and writing them in a different order than they appear. So exactly like what you do, deck of cards, you take a card from the deck and place it somewhere else. If I take the first equation, x minus y minus z equal to 2, take this thing, push it to the last row, so it's going to read like 5z equal to 10, and put this thing in the second equation, so it's going to read like y plus 3z equal to 5. Well, I achieved that coveted look of triangle of zeros down here. Everything has been wiped out, and I can just easily refer to, okay, apply the back substitution, you're done. But of course, as a student who's looking at this thing carefully, we are already done here. We don't need to rewrite one more time. You can actually find the solution. But just to introduce you to a simple topic. First of all, now our new equations are going to be labeled in the same way that the first one was. So this is the new second equation, and this is the new third equation. So this E2 and E3 are children of some equations that we had here, but just not to make it crowded, we are still calling it E2 and E3. From here to here, what happened is that we simply exchanged the location of 2 and 3. That's all that happened. So that's called the exchange operation. This is going to be called addition operation. So this is what we have done here. Multiply an equation by a number and add it to the other one. So this is what we are doing here is called addition, even though it's a lot more complicated than that. It's called addition operation. This operation that we are doing here is has several names like exchange, swap, shuffle, or whatever you want to call it. And then what? Then we come here and say we divide by 5 or multiply by 1/5. So what we are really doing here is we are saying take equation number 3 multiplied by 1/5. That is called multiplication. Well, that is obviously multiplication, or you could say division, but tradition has it to call it multiplication. So when we want to solve the full case, there are 3 operations referred to elementary row operations. Elementary row operations. Elementary row operations multiply some equation. No, it doesn't have to be 1 or 2 or something. Equation number I added to equation number j, for example. Take equation number I, perhaps exchange it with equation number j. Take equation number I multiplied by some number. So these are 3 examples of operations that we do, and that's all it takes to solve linear equation. 3 very simple operation. When it is applied judiciously, it's going to solve the equation for us. We are going to practice how we are going to pack this thing together and carry it out, but you see the sense that is involved. Of course, because of the repetitive nature of this thing and the number of arithmetic operation that is involved, the whole thing is quite error prone. You want to write it very carefully. You want to be able to go back and check it, so you don't want to scratch things, rather you want to rewrite them and be patient doing that. So once you have reached this stage, you have the option of saying, okay, I can apply the back substitution and do it like that. You have a second option. You can say, well, just as I created these zeros here at the bottom, if I go ahead and also create the zeros at the top, then I'll have x, y, z isolated, and then my solution is going to just pop out. Okay, so in the full case, when we are doing elimination all the way here, you can continue with the elimination all the way to the end, implying that what we were doing there, we can do that with elimination as well. Let me go ahead and explain it to you further down. Let me write this thing so that I'm going to start from there and ask you to carry out the steps involved. So let's start this equation. So we have the equation at the end. We have x minus y minus z is equal to 2. Y plus 3z is equal to 5, and 5z is equal to 10. So we are saying, instead of back substitution, use elimination. To solve to the end. And that is sometimes referred to as Gauss-Jordan method. So what we are doing here, sometimes referred to as Gauss elimination method. Gauss is one of the very famous mathematicians, a German mathematician. So he has done very significant works. When a mathematician does something like that, they put his name on some simple activity like this as an honor. Of course, he has done significant more work than that, and this style of solving things had been done several thousand years before Gauss got to it, but it's typical in mathematics to do something like that. Okay, so using the elimination method, so what we are going to do is to reduce this 5 to 1. How do we do that? We say 1/5 of equation number 3. So I'm going to write this. Of course, sometimes you don't write as much, but let me write all the steps so it's clear what we are doing. So I divide by 5. We are going to call it multiplication method, 1/5 of equation 3. Okay, what now? What is now is that I'll aim to eliminate this and that. You tell me. Now again, let's call this is RE1, this is RE2, this is RE3. I aim at eliminating. This is my target. I want to eliminate 3Z. You tell me, what should I do? I don't want to use E1, because if I use E1, then X is going to show up here and I'm going to mess up the zeros I've created. The only option I have is to use this. How do I use this to eliminate 3Z? Okay, so this is your clue for you to actually walk on that bridge and come and catch me. So of course E2 minus, you take this coefficient 3E3, and here what do we do? Take E1 and of course add just E3 to it, and we are going to be when I add this one to that, I get X minus Y, and Z's are supposed to cancel. I get the 4. 3 times this subtracted from that is going to become Y, and 3 times this subtracted from this one is going to be minus 1, and I'll have Z is equal to 2. So these are my 3 equations now. Again, I'm labeling them number 1, number 2, number 3. So of course I have my Z, I have my Y. The only thing I need to get rid of, eliminate this one. Well, the only way to eliminate that is to involve E2, and of course, how do I eliminate it? If I simply add E2 to this thing, what I get is becomes X. Okay, when I add this to this, it cancels out. This becomes 3, Y becomes minus 1, Z becomes 2. So by the time you have eliminated everybody here and you insisted that the coefficients to become 1, you actually solve the equation. You have X, you have Y, you have Z, you're all set. And let's go and see, this is actually what we had a long time ago. X, Y, Z were written like this. 3 minus 1, 2. Now you can have it written in this way as well. It's just items moved around a bit. It's the same answer. So that is the solution of our equation. Okay, so we solved an equation. Forward elimination. We said now we have 2 styles. One is just Gauss method. The other one was called Gauss-Jordan method. Okay, so the Gauss was second stage, solve it by back substitution, and Gauss-Jordan was continue elimination all the way to the end and you're done. In my view, Gauss-Jordan is much neater, cleaner, same idea from the beginning to the end. So I'm partial to the Gauss. Let's call this one. This is the Gauss-Jordan. However, most textbooks like to go two-tone approach, do half of the problem by elimination the other one do it by back substitution. Either way is fine. Okay, so we are done with that. Matrix formulation and augmented matrices. Well, I've said several times we are dealing with the curse of dimensionality. We are writing and writing and writing so much we get tired, and it's very error prone to write a lot. So people try to simplify, just as when you're texting you have all of your own abbreviations and your favorite, I guess, that LOL or whatever. Well, in mathematics we have a lot of abbreviations of that type. We were ahead of you, sorry to say. Well, what abbreviation can we do? You notice that X, Y, Z don't play any role at all. All we care about is first variable, second variable, third variable. So we don't really need to write X, Y, Z. We just need to remember who's first, who's second, who's third. That's all. So if we avoid writing X, Y, Z, all of a sudden we are going to be spending 50% less time in writing. Sometimes in mathematics you do some shortcuts and simplify life and make a notation, but then that notation dictates a new life to you. Very much like new technology. First phone was supposed to help us, but now we are glued to our phone and somehow phones become our masters. Same way here. What we are going to do, take these equations and say, okay, first we want to just reduce the amount of writing we do. So we are brought to the idea of a matrix, plural matrices. So our equation look like X minus Y minus Z is equal to 2. First of all, we insist on writing same variables underneath each other. So if I have X, Y, Z here, second equation cannot be Z, Y, X or anything like that. However, you write the first equation, everybody else is going to line up. So all the dots have to line up. We take this thing. So the only thing that happens here is these numbers are going to change. X, Y, Z stay in their places. So say, okay, don't write X, Y, and Z. Just separate them. This is 1, then minus 1, then minus 1, and then 2. And then I have 3, minus 3, 2, 16. And I have 2, minus 1, 1, 9. So it means that this was X, this was Y, this was Z. This one, you might call it the right hand side. Sometimes you might signal it by putting a bar here to indicate that was the left side, that was the right side, so long as you know what you're writing. Typically this whole part has a name by itself. It's called the coefficient matrix. And this one, as we said, has a nickname, is a right hand side, simply because most often it's just on the right hand side. The whole thing then is called the augmented matrix. So augmenting, of course, means adding something to something. Augmented matrix. Okay, what you want to do is to practice these ideas in the context of a few examples. In the next section we are going to make a cleaner representation of this thing, give a bunch of new definition. Most important of that would be the so-called echelon form, and then we'll be on our way for solving equations of much bigger size, and perhaps introduction to how to use certain software to do this. Okay, until next time, good luck and God bless.